Okay, in this problem we have a three-step process for an ideal gas contained by a cylinder with a movable piston. So the gas starts at a temperature and pressure of these original conditions, T naught, P naught, V naught. And there are three steps that are described, and what's asked is for the PV diagram, isotherms, and then to kind of comment on each step, whether or not work is done, heat is exchanged, etc., how the internal energy changes. So we've got an ideal gas. We know that the ideal gas follows this relationship, PV equals nRT, or P is equal to nRT over V. So essentially we know that if we were to draw isotherms, that would look like something like this, where this is one particular temperature. If we had a lower temperature, it would look like this, and we would get a series of isotherms that looked like this. Okay, so this would be decreasing temperature. So let's see. Let's go ahead and apply these three processes. Step one, cut the volume in half. So you start out some P naught, V naught, T naught. I'll just I don't know where to put it. I'll just kind of stick it right. Well, actually, I'm going to go ahead and make a new graph of this. So let's remember this. The first step is cutting the volume in half, isobaric process, and that means delta P equals 0. So I've drawn up a graph here to use. Here's our original pressure, original volume. It's isobaric, so we know that we're going to do this transition at the same pressure. So we're going to cut the volume in half, and let me just increase, here we go, the size so you can see this. So cut the volume in half, so we're going to go roughly somewhere, I'm going to make it go all the way to this line just so we have something to look at together. So let's just say that this new volume is 1/2 the original volume. So this guy right here is, let's just call this 1/2 V naught, our original volume. Okay, so that's step one. So I should probably label this with a 1. That's our step one. Step two is that we use an adiabatic process. This was isobaric, adiabatic, to bring the system back to the original volume. Okay, so we know that step 2 being an adiabatic process. I'm going to change the color here. So original volume, we're going to go back to this volume. Adiabatic means that the heat transfer is 0. So if we double the volume and there's no heat transfer, we know that we actually will lose temperature. So we'll get back to that same volume, but the temperature will be lower since the temperature increases in that direction. I'm just going to, this is the temperature they're at now. Here's where we're at. We're going to be at a lower temperature. So I'm just going to pretend like that takes us down to this dot right here. So that's step 2, the adiabatic expansion to the original volume. Now step 3 is an isochoric. We know that's delta V equal to 0. It brings it back to the original pressure. Okay, so let's go to the isochoric, to the original pressure. I'll use this pink. So isochoric means it's going to be along this line, kind because there is no volume change, and we're going back to the original pressure. So that's our third step. Now that we've done all those steps, the question now becomes what. Well, we've drawn the PV diagram carefully, I hope, and then in each step assess whether heat is absorbed, given off, work is done on the gas, by the gas, and if there's a change in internal energy. So our questions are, I guess I should kind of track those. The questions are, is work done by or on the gas? That's our first question. The second question is heat into or out of gas. And then the third question is what about the internal energy? How does that change? Okay, so just as a reminder, you know that internal energy, the way that is measured is strictly through temperature. So temperature gives you an indication of that. So the temperature goes down, the internal energy goes down. So let's start out by asking ourselves in step 1, do we have work done on the gas or by the gas? So we're going from, and the kind of work that we're talking about is the pressure, changes in pressure and volume. So the pressure is constant, and then the question is, how does the volume change? Well, the volume is cut in half. Now, in order to do that, the gas must be compressed. Therefore, in step 1, we have the condition where the work in step 1, right over here, 1, we have work on the gas. Work is done on the gas in order to compress it, but it happens at under isobaric conditions, so the pressure doesn't change. Well, if you shrink the volume in half with no change in pressure, normally if you shrunk it in half and you would get a pressure increase. But to keep the pressure constant, you'd have to actually reject a lot of heat. So the second question, we have that Q goes out of gas. And then the third question is, how does the internal energy change? Well, if Q goes out of the gas, we are expecting the temperature to drop, and you can see that we're on an isotherm that's actually lower in temperature than the original. So the third one is that delta U is less than 0. It's negative. Okay, so this is in step 1. So this is our first. This is step 1. Now, what about step 2? Step 2. Let's go here. I'll write that down. Step 2. We go from here to here. Now, that involves a doubling of the volume. And then the question is work done by the gas or on the gas? The pressure changes and the volume changes. So since the volume is increasing and the pressure is, the pressure is decreasing, the volume is increasing. What would that mean? On the gas, by the gas. Okay, so I guess I would have to actually figure out myself if the product of this state is, the second state is more or less than the product of the first state. So in order to figure that out, so P, the work is P2 V, I guess we're going to call it V naught, equals or minus P naught times 1/2 V naught minus 1/2 P naught V naught P2 V naught. Okay, so that is the work. If this term is bigger than that, then we know that the gas does work. Can we figure that out? Let's see. Oh, wait. Here's something else, too. We know that the work done is essentially the area under this curve. This equals the work that's done. So the area is it's integrating the differential of PV, or P differential of integrating P delta V. This equals the work. Now, is it done on the gas or by the gas? Well, I'm going to skip that for now. I don't know the answer. Second question: heat into or out of gas. I know the third question that is that the temperature once again drops, and since this one is a 80, it's no, it's not isothermal. It's adiabatic, so that means there is no heat exchange. So the second question is Q equals 0. And the third question is internal energy delta U therefore drops. Well, then I would say that given this information, that the gas must be doing work in order for its internal energy to drop. I would say that the gas does work. So, but we know that the internal energy equals the Q plus W. If Q is 0, then the internal energy change equals the work. Oh my gosh, here's the convention. The work done on the gas. So since the work is done, delta U is the work done on the gas, and we know delta U is less than 0 because the temperature drops. Therefore, we know that the work done on the gas is negative, or that the gas does work. Wow, I hope you followed that reasoning. You might have to rewind. I could barely follow it myself. I'm just so sleepy. Okay, I cleaned this up a little bit. So hopefully you can see it a little bit easier. And then our last question. So we've got 2 delta. Okay, so I did 3, 2, 1 this time. Third question: internal energy is less than 0. Q is 0. Therefore, work is done by the gas. And then our third situation. So we have that it's isochoric, so the volume doesn't change, but we do get an increase in pressure. So the PV work that is done, I think it's none. P delta V is 0, so the work is, there is no work that is done. But what about, we do actually increase in temperature from this isotherm to this isotherm. So that means that Q is into gas. And the third thing is that what about the internal energy? We know the internal energy change is greater than 0 since the temperature increases. So